Welcome to MRL. This is the third part of the study of rational numbers, the properties of rational numbers. Now, in this learning session, we'll be learning about the other properties of rational numbers. Now, let us consider the commutative property of addition of rational numbers. If a and b are rational numbers, then a plus b is equal to b plus a. It means that rational numbers can be added in any order, the sum is the same. Let us consider an example. If I add 8 by 11 and minus 16 by 9, then by following the rules of addition, I'll get minus 104 by 99. Also, if I add minus 16 by 9 plus 8 by 11, again I'll get minus 104 by 99. That means the values are the same. Therefore, commutative property of addition is closed for a set of rational numbers. That means rational numbers can be added in any order, the sum is the same, and therefore the commutative property of addition is closed for a set of rational numbers. Now let us talk about the commutative property of multiplication. If a and b are rational numbers, then a cross b, that means a multiplied by b, is same as b multiplied by a. That means rational numbers can be multiplied in any order, the product is the same. Let us take an example. 8 by 11 is a rational number, minus 16 by 9 is another rational number. When we multiply the two rational numbers, we get minus 28 or 128 by 99. So also minus 16 by 9 into 8 by 11, I get minus 128 by 99. Therefore, the commutative property of multiplication is closed for a set of rational numbers. Please remember that. Now let us talk about the distributive property of multiplication over addition. And we know what is distributive property of multiplication over addition. And that is, if a, b and c are three rational numbers, if I add b and c and multiply by a, or multiply a into b plus a into c and then add, the answer is the same. That means LHS is equal to RHS. Let us understand this with an example. Now 2 by 3, 1 by 2 plus 1 by 9 are three rational numbers. Now I have grouped 1 by 2 plus 1 by 9 and multiplied by 2 by 3, followed the procedure of addition and multiplication, and I got 11 by 27. And so also when I take 2 by 3 and multiply by 1 by 2, that is 2 by 3 into 2.5 plus 2 by 3 into 1 by 9, by simplification we get again 11 by 27, that is LHS is equal to RHS. Therefore, it satisfies the distributive property of multiplication over addition, and which is very much closed for a set of rational numbers. Now let us talk about additive identity. Already we know what is additive identity. Additive identity is 0, and here 0 by 1 is a rational number. So a is a rational number, 0 by 1 is a rational number. When we add, we get a. That means when a rational number is added to 0, again we get back the same rational number. Therefore, additive identity is closed for a set of rational numbers. Now coming to the next important property, that is multiplicative identity. We already know the multiplicative identity is 1. If a is a rational number multiplied by 1, again we get back the same rational number, that is a. That means 11 by 12 is a rational number. When multiplied by 1, we get again 11 by 12, and therefore multiplicative identity is closed for, or exists for rational numbers, or is closed for rational numbers. The next important property is additive inverse. We already know what is additive inverse. When a is a number and minus a is its additive inverse, when we add them, that is when a is added to minus a, we get 0. The minus a is additive inverse of a is additive inverse of minus a. So please remember that, and this is closed for a set of rational numbers. Now to understand this, let us take an example. 8 by 13 is a rational number. Its additive inverse is minus 8 by 13. When I add 8 by 13 to minus 8 by 13, I get 0, and therefore additive inverse exists or is closed for a set of rational numbers. Now multiplicative inverse. Again we know what is multiplicative inverse. We know that if a is a rational number, then 1 by a, that is the reciprocal of a is 1 by a, is called as the multiplicative inverse or reciprocal of a, and when we multiply, we get the product as 1. And mind you, the product 1 is always positive. Now 1 by a is called as the multiplicative inverse of a. The product of rational number and its multiplicative inverse is always plus 1. Please remember, it is always plus 1. For example, 7 by 5 is a rational number. When I multiply by its reciprocal, that is 5 by 7, by changing the numerator and denominator, we get 5 by 7. When we multiply it, we get 35 by 35, which is equal to 1, which is 100% true for a set of rational numbers. Therefore, multiplicative inverse is also closed for a set of rational numbers. So please remember that. Now, the next very important discussion is about types of decimal expansions. We already know what are decimal expansions. Now we have different types of decimal expansions, and they are the terminating decimal expansion, non-terminating recurring decimal expansions, which are two of them, pure and mixed. We'll be learning about it. Then we have the non-terminating, non-recurring decimal expansions. Let us learn one by one and understand them. Now let us consider the first one, that is terminating decimal expansion. So if I have a rational number 2 by 5, if I divide 2 by 5, we get 0.4, and it is ending, that means it is terminating. 0.4 is 100% a terminating decimal expansion. If I take another example, 4 by 125, if I divide 4 by 125, I get 0.032, again it is ending or terminating. So this is called as the terminating decimal expansion. So remember, the decimal expansion which has definite decimal places, there are definite places here, 3 places here, 1 place here, then it is called as a terminating decimal expansion, and therefore 2 by 5 and 4 by 125 are having terminating decimal expansions. And very interestingly, 2 by 5 is a rational number, 4 by 125 is also a rational number. Therefore, rational numbers have decimal expansions which are terminating decimal expansions. Please remember that. Now coming to the non-terminating recurring or repeating decimal expansions. If I divide 1 by 3, again is a rational number. 1 by 3 is a rational number. When I divide 1 by 3, I get 0.3333 and less. It continues. It is not ending here. So therefore, instead of writing 0.3333, we put a bar over 3, indicating that it is repeating. And mind you, 0.3 bar belongs to Q. That means 1 by 3, if it belongs to rational number, is a rational number, then 0.3 bar is also a rational number. Very interesting. Therefore, it means it's very clear that decimal expansions which are non-terminating, recurring or repeating also represent rational numbers. The bar above 3 indicates the repeating part. The decimal expansion has indefinite repeating decimals. That means it is an unending here. Therefore, it is called as indefinite repeating decimals, and it is a non-terminating recurring decimal expansion. The decimal expansion after the decimal point here has only repeating part. See, if you observe here, it is a repeating part. After the decimal point, it is repeating 3333, and therefore it is called as a pure decimal expansion. Mind you, it is a non-terminating repeating decimal expansion, but a pure what you call decimal expansion, because exactly after the decimal point there are numbers which are continuously repeating. Let us take one more example. 2.2525. You see here 2525 is repeat. This is called a non-terminating recurring decimal expansion. Here 2525 is repeating, therefore 2.25 bar, and therefore this is what is called as a pure decimal expansion. Now here also 142,857, 142,857 again repeating, that means 0.14257 bar are pure non-terminating repeating decimal expansions. So please remember that. Now let us take an example, 0.256262, and mind you, this is a non-terminating recurring decimal expansion, or definitely a rational number, but you observe a very different thing here. Here 0.25 is not repeating, 6262 is repeating. Therefore, this is a non-repeating part, this is a repeating part. Therefore, this is a decimal expansion which is non-terminating recurring but impure decimal expansion. It's a impure decimal expansion because it has both the non-repeating part and the repeating part. So please remember that. The non-terminating recurring pure decimal expansions and the non-terminating recurring impure decimal expansions, all of them represent rational numbers. Please remember that. Therefore, we can even define decimal what you call rational numbers as a number which has decimal expansions which is terminating or non-terminating recurring, pure or mixed decimal expansion. okay, is a rational number. So rational numbers can be defined in two ways. A number of the form p by q where p and q are integers and q is not equal to 0 is a rational number, or we can even say a number which has decimal expansions which are terminating or non-terminating, recurring, pure, or what we call mixed decimal is what is called as a rational number. So please remember that. Now we have the decimal expansions of rational numbers and its parts. The decimal expansions of rational numbers, as we have already learned, has three parts: the integer part, the impure part, and the periodic part. Let us understand this very clearly. Now let us consider the decimal expansion 6.15323232 and so on. Rather, it is 6.1532 bar. Now 6 is the integer part, the first part. The 15 is the impure part, which is a non-repeating part, and 323232 is a periodic part, it is a repeating part. Now if you observe here, the string of digits in periodic part is called as the length of the period. It's called as the length of the period, and the length of the period is 100% is 2 here. It is 2. 1 and 2 is the length of the period. So please remember that. Now let us take one more example. 0.333 is 0.3 bar. It is 100% from after the decimal point only 3 is repeating, and therefore it is it's a pure non-terminating recurring decimal expansion. The length of the period is here 1, and it is purely periodic. Please understand, it is purely periodic. Now let us take this example, 0.00430. Now observe here very carefully, 004 is non-repeating, 0000 is repeating. Therefore we have the non-repeating part, which is called the impure part, and the repeating part, which is having a periodic part or a pure part, and the length of the period is 1. Again, that also represents a rational number. Let us take one more example, 0.153232. Here 15 is non-repeating, 32 is repeating, therefore 32 bar. So therefore this is called as what you call eventually, it is called as eventually periodic. So this is purely periodic, this is eventually periodic, this is also eventually periodic. Therefore remember that the rational numbers have decimal expansions that are terminating, non-terminating purely periodic, and non-terminating eventually periodic. So that is what is some of the important properties of rational numbers we have learnt. So go through all the three parts of the study of rational numbers. In the first part we have studied some properties, second part we have studied some properties, and the third part, which we have just discussed, also has important properties of rational numbers. Please follow the method I have already told you. Please listen to what I speak, read what I have given, and repeat reading and listening, and take a book and note down everything in the book, scribble in the book, so that it will be a reference for you to learn about the rational numbers. So thank you. Good day.